10 dimensions. People hear this and they go quiet in a reverent way, like you've said something sacred. The 10th dimension. String theory requires it. Some physicists believe it. Therefore, it must be profound, mysterious, beyond ordinary minds. I want to tell you what's actually going on, because the story is more interesting than the mysticism, and the honest version has a problem at its center that nobody in the popular accounts wants to sit with very long. Let's start with what a dimension is, not what it sounds like, not the science fiction version, what it actually means operationally. A dimension is a direction in which something can independently vary. That's it. If you're sitting in a chair, you need 3 numbers to say where you are. How far from the wall, how far from the floor, how far from the window. Change one number without changing the others, and you've moved in 1 dimension. 3 coordinates, 3 dimensions. This isn't philosophy, it's bookkeeping. You need exactly 3 numbers to locate any point in the space we inhabit, and no arrangement of 2 numbers will do. That's what makes it 3-dimensional. Now here's the thing about bookkeeping. You can do it with more columns if you want. Mathematicians do this all the time. A 10-dimensional space is just a space where you need 10 independent numbers to locate a point. There's nothing mystical about it. I can write down the equations right now. The math generalizes perfectly cleanly from 3 to 10 to 1,000 dimensions. The mathematics does not care. The mathematics never cares. The question is whether the mathematics corresponds to physical reality. And that's where the story gets genuinely interesting and genuinely uncomfortable. Here's the situation as it developed. By the 1970s, we had quantum field theory working beautifully for 3 of the 4 fundamental forces: electromagnetism, the weak force, the strong force, all unified into what we call the Standard Model. The mathematics predicted experimental results to 12 decimal places. Richard Feynman, me, helped work out the electrodynamics part, and I'll tell you it was a strange, beautiful business. You calculate the magnetic moment of the electron, and you get 1.00596518. You measure it in the laboratory, and you get 1.011596521.8. Agreement to 11 significant figures. That's not a coincidence. That's a correct theory. But gravity kept refusing to fit. Every attempt to quantize gravity, to write down a quantum field theory of gravitation the way we did for the other forces, produced answers of infinity, infinities everywhere, and not the manageable kind that we knew how to cancel. The mathematics simply fell apart. In 1984, Michael Green and John Schwartz were working on something called string theory, which had been kicking around in less successful forms since the late 1960s. The central idea is that the fundamental objects in nature are not point particles, little dimensionless dots, but one-dimensional extended objects, strings, incredibly small ones, on the order of 10 or 35 meters, the Planck length. You cannot build an instrument to see this directly. The Large Hadron Collider probes distances of about 10 or 19 meters. We're 20 orders of magnitude short. Now, when Green and Schwartz worked out the mathematics of these strings vibrating and interacting, they discovered something strange. The equations were only consistent, only free of certain mathematical pathologies called anomalies, in a specific number of dimensions, not 3, not 4. 26 dimensions for bosonic strings, or 10 dimensions for superstrings, which also incorporate supersymmetry, not approximately 10, exactly 10. This is the part that's genuinely surprising and genuinely demands an explanation. You don't get to pick the number of dimensions. The mathematics forces it on you. If you try to write the superstring equations in 9 dimensions or 11, you get mathematical inconsistencies. The theory self-destructs. Only in 10 does it hold together. That's a real result. It's not numerology. So, where are the other 6 dimensions? The standard answer is compactified, rolled up, curled into structures so small, again, near the Planck scale, that we can't detect them directly. The shapes these 6 dimensions form are called Calabi-Yau manifolds, after Eugenio Calabi, who conjectured their existence, and Xingtung Yau, who proved they could exist mathematically. These are complex geometrical objects. They have holes in them, topological features, and the number and type of holes determines, in principle, the particle spectrum you'd observe in the 3 large dimensions. The masses of particles, the coupling constants, all of it, shaped by a geometry we cannot see. Now, I want to pause here because I think this is where honest explanation has to say something uncomfortable. There are an enormous number of possible Calabi-Yau manifolds. Enormous. Estimates range, but the number of distinct compactifications, Distinct ways to curl up those 6 extra dimensions is something like 10^500. That's not a typo. 10 to the 500th power. The total number of atoms in the observable universe is roughly 1080. The number of possible string theory vacua, each one corresponding to a different universe with different physical constants, different particle masses, different forces, is so staggeringly large that it exceeds any physical quantity we know how to name. This is called the landscape. Leonard Susskind coined the term. And it's a problem, a serious one. Here's why. In physics, when a theory predicts something, you test it. When quantum electrodynamics predicted the electron's magnetic moment, we measured it. When general relativity predicted the deflection of light around the sun, Arthur Eddington measured it in 1919, got 1.75 arcseconds, matching Einstein's calculation. The theory made a specific, falsifiable, testable prediction, and reality confirmed it. String theory, as it currently stands, does not unambiguously predict the particle masses or coupling constants we observe. It can accommodate them. Somewhere in that landscape of 10^500 vacua, presumably some patch has our physics. But can accommodate is not the same as predicts. A theory that can predict anything predicts nothing. Some physicists respond to this with the anthropic principle: most of those 10^500 vacua produce universes where stars don't form, or atoms don't hold together, or some other condition necessary for observers doesn't hold. We necessarily find ourselves in one of the habitable patches. This is logically coherent. It may even be true. But it makes me nervous because it's a style of reasoning you can apply to explain almost anything after the fact. That's not how I think good physics works. I want to be scrupulously honest here. I am not telling you string theory is wrong. I genuinely don't know if it's wrong. Nobody does. This is not false modesty. The theory has produced real mathematics, real insights into geometry and topology that mathematicians care about independently of physics. The ADS-CFT correspondence discovered by Juan Maldacena in 1997 connects string theory in certain curved spacetimes to quantum field theories without gravity, and it's been extraordinarily productive. These are genuine results. What I'm telling you is that we don't have experimental confirmation. We don't know if the extra dimensions exist. We have theoretical consistency requirements that force them into the mathematics, and we have no instrument capable of probing the scales where they'd be hiding. The Planck length is 1.6 times 10 bars to 35 meters. To probe it directly with a particle accelerator, you'd need a machine roughly the size of the Milky Way galaxy. We're not building that. There are indirect tests people have proposed. If extra dimensions exist at scales somewhat larger than the Planck length, some models have them at 10^18 or 10^19 meters, the LHC might detect deviations from the inverse square law of gravity or produce Kaluza-Klein particles, which are excitations of standard model particles in the extra dimensions. The LHC has been running since 2008. The hints that were hoped for haven't shown up. This doesn't rule out extra dimensions. They might simply be too small, or the signatures might be too subtle. But it constrains the possibilities. Let me tell you about Theodore Kaluza, because his story is important and usually told incorrectly. In 1919, the same year Eddington was measuring starlight bending around the sun, Kaluza sent Einstein a paper. The idea: what if there were a fourth spatial dimension, curled up small, in addition to the 3 we see? He wrote down Einstein's equations of general relativity in 5 dimensions, 4 space plus 1 time, and then looked at what fell out when he assumed nothing depended on the extra coordinate. Remarkably, out dropped Maxwell's equations of electromagnetism. Gravity in 5 dimensions with 1 dimension curled up automatically contained electromagnetism in 4 dimensions. Einstein sat on the paper for 2 years before agreeing to submit it for publication. I don't blame him. The result is almost too pretty. A 5th dimension you can't see produces the force that gives you light. And in 1926, Oscar Klein worked out that if this dimension were curled into a circle of radius around 10 or 35 meters, it would be completely undetectable at any energy scale available to experiment. Kaluza-Klein theory, as it's now called, was the first serious proposal that extra dimensions could be real and hidden. It didn't work as a complete theory, it couldn't incorporate quantum mechanics properly, and it didn't account for the other forces we subsequently discovered, but the conceptual machinery it introduced is exactly what string theorists use today. The idea that dimensions can hide by curling up, that the geometry of hidden spaces determines observable physics, that's Kaluza's insight, 70 years before string theory needed it. Here's what I find genuinely interesting about the 10-dimension result. It's not that someone decided 10 dimensions would be elegant or mystically significant or satisfying. Nobody chose 10. The mathematics chose it. You write down the most consistent quantum theory of relativistic one-dimensional extended objects with supersymmetry. You demand mathematical consistency, specifically the cancellation of anomalies, and 10 falls out. The calculation forces it. This is how physics is supposed to work when it works. Nature forces answers on you. The quantization of energy wasn't something Planck chose because it was philosophically pleasing. He found it was the only hypothesis that fit the experimental data for blackbody radiation. In 1900, he called his own result an act of desperation. The discreteness was forced. Similarly, Einstein didn't decide that time should dilate and lengths should contract because he found it aesthetically satisfying. He took two experimental facts, the constancy of the speed of light and the principle of relativity, and followed the mathematics to where it led. He didn't like all of it at first. Reality doesn't care what you like. So when the mathematics of superstrings forces 10 dimensions, not 9, not 11, not 17, that's at least evidence that you've found some kind of consistency. You found a theory that doesn't immediately contradict itself. That's non-trivial. But consistency is not the same as correctness. Ptolemy's model of epicycles was internally consistent. It could calculate planetary positions. It was wrong about what was actually going on. The history of physics has consistent theories that turned out to be effective descriptions of something else, approximations to deeper truths. Newtonian gravity is consistent. It works extraordinarily well for most purposes. It's an approximation to general relativity, which curves space-time in a way Newton's flat space gravity cannot capture. Newton didn't know this. He had no way to know. His theory was successful and wrong about its own foundations. String theory might be like this. It might be a consistent framework that captures something real about nature at some level while being wrong about the fundamental picture, or right about the mathematics and wrong about the physical interpretation. We don't know. I am not saying this to be dismissive. I am saying it because it's true and you deserve to know it. The honest position is this. We have a mathematical framework that requires 10 dimensions for internal consistency. We have no experimental evidence for those dimensions. We have one candidate theory of quantum gravity among several, and the others, loop quantum gravity, causal dynamical triangulations, asymptotic safety, don't require extra dimensions at all. Loop quantum gravity works in 4 dimensions. It has its own severe problems, but extra dimensions aren't among them. What we have is a genuine puzzle. Gravity refuses to fit into quantum mechanics using our standard tools. Something has to give. String theory gives you extra dimensions and a landscape of 10⁵ possible universes. Loop quantum gravity gives you a discrete space-time at the Planck scale and different mathematical headaches. Neither is confirmed. Both might be completely wrong. The correct theory of quantum gravity might look like nothing anyone has proposed yet. This is where explanation honestly ends, not because the question is unanswerable in principle, I believe it's answerable, but because we haven't answered it yet. We lack the experimental access. The Planck scale is genuinely beyond reach with current technology by an enormous margin. We may get indirect evidence. Cosmological observations, the cosmic microwave background, gravitational wave detections, might eventually show signatures of extra dimensions or rule out their existence in certain mass ranges. The LIGO collaboration and its successors are probing space-time at a level of precision, measuring length changes of 10 or 18 meters. That was unimaginable 50 years ago. The game continues. I want to leave you with the thing I think is most interesting about all of this, and it has nothing to do with mysticism. The fact that a theory of everything, a theory consistent enough to unite quantum mechanics and gravity, appears to require the universe to have more dimensions than we observe is not a failure of the theory. It's a genuine discovery about how hard the problem is. 3 dimensions aren't enough. The geometry has to be richer. Whether string theory is the right framework for that richer geometry, we don't know. But the question, why these dimensions, why this geometry, why these forces and not others, is a real question with a real answer somewhere, waiting for someone to find the right tools to reach it. And the right tools probably don't exist yet, which means someone is going to have to invent them. That's what I find exciting. Not the 10 dimensions, the fact that we can see the problem clearly enough to know we're stuck, which means we're close enough to the edge to fall off into something genuinely new. That's where physics has always moved. That's where it's going to move again.